Okay. So based on the data that I give to you, we have the height and weight, and you can select the distributions. Okay. And let's say now I'm looking at the height. You can make a different pin width. Okay, so the pin width means you want to make the range of the height. If it is 100, then it is between 0 until 100. It will be in 1, and the other is 100 until 200. It will be in one range. You can make it lower. Let's say this is in between 10. Pin width is 10. So it will be every 10. So 90 until 100, 100 until 110, 110 until 120, and so on. Okay. And then there is one fitted distribution here. It will give you the distribution way. Let's say this is the normal distribution. Okay, if it is known, then you will see only the bar. But if you are going to fit this data into a distribution, yeah, you will see this is the normal distribution. Actually, you can also look at the other distribution like beta distribution, okay, or gamma distribution, or yeah, something like this one. They can plot and they can give you these numbers, okay? But I do not want to discuss which is better for this data. Maybe this is the more representative, the kernel density distribution. But based on the common sense, okay, I can say that it is still somehow normal distribution, but it is a little bit skewed. Okay, skew to the right, and we call it, this is the negative skew. And maybe there are some questions before. If you look at this one, the mu is 161. Maybe not that. Let's see this one. Maybe it's better. The weight, okay, because it is in the middle. Yeah. So the mu is 66.35. So this is the mean of the population. But what about the median? You can open the feature statistics, or you can open the box plot. Yeah, it's up to you. So the mean is 66.35, and then the median is about 66. So as we learned before, we have a symmetrical distribution. It is not exactly in the same number, but it's almost. Okay, so we can just say this is still symmetrical distribution. It is just to represent that the mode, median, and mean is almost in the same line. But it doesn't mean that it is always exactly the same. Median and the mu should be the same. No, it's almost okay, or yeah, similar or equivalent. Okay. Thank you for your questions. So there are many good questions. Okay. So I like that kind of question. So give me a lot of questions so I can give you more understanding. What we learned before, it was about the chi-square. What we learned was about the chi-square calculation on the coins. In the real situation, we can see some example like this one. This is example from the book. We have two categories. We have the attribute about whether the person like the science fiction or not, and whether the person play chess or not. So there are two categories: like science fiction and not like science fiction. And then play chess and not play chess. Maybe if in the data, it like representing the something like this one. Person one, science fiction. Maybe true. Okay, so true means the person like science fiction. And then chess is one, maybe true. So he or she play chess. And based on these numbers, based on this data, we would like to make something like table. So how many people who like science fiction and play chess? And we know there are 250. And we also check the person who likes science fiction and not play chess. We have 200. The person do not like science fiction, there are 50, and the person who do not like science fiction and do not play chess, there are 1,000. Okay. So the chi-square calculation and the number in the parentheses are the expected counts. Okay, so this number 90 is the expected count. I know those numbers, so I expect that the person who likes science fiction and the play chess is 90, but the actual value is 250. Okay. Based on these numbers, we can calculate the chi-square. We just put the 250, which is the observation value, minus by the expected value, minus divided by the expected value. And we sum all those numbers. So we have 50, which is the observed value, minus by 210, which is the expected values, divided by the expected value. And then we find the numbers. 507.93. 507.93. Is it high or low? Compared to the previous example, it is high. Okay. The previous example about the coin, we have very low numbers, 0.16. Okay. This is just example. Maybe if you want to practice, you can use this one. So this number is very high, 507. So the higher means there is a correlation. So we can say that the like science fiction column and the play chess column are correlated. That's it. You can say just correlated. But do not assume many things. Okay? Maybe you will think that, okay, maybe someone who likes science fiction, they are really playing chess. Yeah, you can say that one, but do not assume anything. So we just say based on the statistics, they are correlated. There might be some other variables to indicate the correlation. So we can use this one for the nominal data. Now, we can also use the correlation for the numerical data. In the correlation coefficient based on the numerical data, there is one measure, we call it person product moment coefficient. Person product moment coefficient. This is the formula. It's a little bit long to explain. We can also use this formula. Maybe it will be easier to understand this formula. But you can also use this formula by looking at these numbers. Yeah. The A means one column or one tuple. B is another tuple. And this bar represent the average. So the numbers will be minus by the average. The number in the column B will be minus by the average. And then we will do the summation. And it will be divided by the standard deviation of the column A and the standard deviation of the column B. And then we will multiply with the number of data minus 1. Or we can have this formula, it will show the same. Usually we will show it in the formula as R. R is represent the person product moment coefficient. If it is higher than 0, so the two dimension or the two tuples are positively correlated. It means when the A value increase, B value also increase. The higher value is the stronger correlation. Usually the maximum will be 1. Okay? So if it is almost 1, it is strongly correlated. But if the value is 0, it means the two data are independent. There is no correlation. If the value is less than 0, then it is negatively correlated. I give you an example. There is one agriculture research organization. They are testing a particular chemical fertilizer to try to find out whether an increase in the amount of fertilizer used would lead to a corresponding increase in the food supply. I don't know what is the Korean of chemical fertilizer. So if you make a plant, okay, so you will put some fertilizer to make it grow faster. Okay. So this research organization, they want to know if they put like 2 units, they can produce 4. If they put the fertilizer 1 unit, they produce 3 units of the product, and so on. So they want to know whether the X and Y are correlated or not. The easy way to calculate this one is to get this one. The total X, it means we want to do the summation from this X, and the summation of Y, we want to do summation for all this Y. And then we have another variable, which is X multiplied by Y. It is 2 multiplied by 4, 8. 1 multiplied by 3 is 3. 3 multiplied by 4, it is 12. And we also measure the X square and Y square. So 2 square is 4, and the 4 square is 16. And then we will do the summation. We will do the summation. We will do the summation. After we do all the summation, we can calculate the R value. So this R value is, you can just fit all those number. N is the number of the data, this is 7. And then multiply by the summation of xy. Summation of xy is 93 minus by summation of x multiplied by summation of y. And then divided by the square root of this one. So you can put all those number into this. And after that, you can look at the numbers, then you will find the R value is 0.811. This on the definition. Is it high? Is it positively correlated or not? Based on the definition, if it is higher than 0, it is positively correlated. And because it is almost 1, we can say it is very highly correlated. You can use the widget correlation in the orange. Okay, I still use this iris as the example. Okay, in the correlations, we can see the correlation between two numerical attributes. Here we can see there is a high correlation between the petal length and petal width. There is a high correlation between the petal length and sepal length. And there is a high correlation between the petal width and sepal length. However, we have some negative correlation. Okay, it shows negative 0.4, negative 0.35, and negative 0.10. In orange, they have another way to calculate the correlation. We have the Spearman correlation. I think it is enough to just understand the Pearson correlation. When we do the evaluation of this correlation, we can look at the visualization. If we have this line, it seems that the correlation is negative, -1. If it is like this one, then it is positive correlation. 0 means we cannot see any pattern. The increment of x does not represent the increment of y. Y. So if there is a slightly high correlation or 0.8, we can see something like this. You can also see this kind of things in the scatter plot. Here. Today I will explain this scatter plot a little bit later. But you can take a look. In the correlation, we can see that the petal length and the petal width is highly correlated. So I would like to make the scatter plot, petal length, and the petal width. And you will see that, it has a high R value. You can also give this regression line. If you click this one, so in the orange, it will show directly about the R value. So the green color is the R value for the only iris virginica. The red color, it is about the R value for this iris versicolor, and the blue color is only for the iris setosa. But the black color, you can see this is 0.96. Okay? It is for the whole data, for the population data. Yeah, you already see the data that if it is increasing from X to, if there is an increment on X and it follows the increment on Y, it is the positively correlated. If the increment of X follows by the decrement of Y, it is negatively correlated. But there can be a double correlation. In one until half, it is increase, but after half, it decrease. So the half fragment is positively correlated, and the right half is negatively correlated. It is also possible. Maybe you will see this kind of graph like the product. Product have life cycle. Maybe now it is getting popular, so it is increasing. But until a certain point, the product selling will be at the top, and then it goes down. So yeah, it can be represented with this kind of data. If the data are uncorrelated, then there is no pattern. This is the uncorrelated data. There is no such pattern that the increment of X will follow the increment of Y. This also, the increment of X just still on this area, or the increment of X, it is still on this area. So there is no correlation between the two data. Okay, so what is the purpose to do the analysis on central tendency? We want to check the distribution of the data. We want to check the dispersion of the data. We want to get the mean, median, and the mode to see how the data is represented. What are the components of the 5-number summary? What are they? Yeah, minimum, Q1, median, and then Q3 and maximum. Okay, so please remember this one. A box plot can represent 5-number summary. True or false? True? Okay, then yeah. So this is the end of the first PowerPoint. Let's go to the second PowerPoint. So in this slide, I think I will make it quick, because some parts is just to show you about the data visualization. So we are going to see the basic of visualization and some exploratory data analysis with the visualization. What is data visualization. Maybe you know already, data visualization means you want to make it as a graph. You want to plot the data. You want to make a bar chart. You want to make a histogram. You want to make something beautiful. Okay. But why? We need to do data visualization. We want to gain some insight. And the information space should be represented in the graph. Because if just showing the numbers, we cannot understand at all. And it will provide the qualitative overview of large data sets. And it will search for patterns. Or we can see the trends. Or maybe we will see the structure, the irregularities, relationships among data. And it helps find interesting regions and suitable parameters for further quantitative analysis. So usually the data visualization will be done at the first time when you want to perform your data analysis. Some of the categorization mentioned by the book. Okay. I bring the book, so it's very thick. If you want to buy the books, okay. If you do not want to buy the books, so I just put all the contents in the PowerPoint. So you can just use the PowerPoint. There are 6 types of the visualization. Because our course is not about the data visualization, maybe I will just give you some idea what are the data visualization techniques until now. We need to understand the basic one. Until now, you already learned some basic like bar chart. The bar chart, it is important to reading numbers. And then it is to compare the individual bars to each other. And it may explore the overall trends across the categories. The data of the bar chart will be one or more text or categorical variables and one numerical variable. For example, here we distinguish between male and female. So it is categorical. Okay. And then we have unknown occupation, person without specified occupation, person working and dealing in general, blah, 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 maybe organization. Okay. So the title is about male and female occupations from the 1881 census of England and Wales. So this is the census data. It means maybe it is related with the occupation of male and female in the England and Wales. And we want to check how many people who are under a certain occupation. In this case, I know that many people are in the agriculture for male, but for female, it is unknown. Maybe they cannot describe their occupations. Histogram. In the histogram, it is different with bar chart. What is the difference? In the bar chart, you will plot the categorical. But in the histogram, you will plot the numerical. Okay. That's the most significant difference between the bar chart and the histogram. For example, this is the head of black cherry trees. So you can see the trees, and then we collect the data. What about the head of the trees? And yeah, there are the trees, so we can collect the data in the table. Like say the tree number 1, the head is 63. The head number 2, for example, 75, and so on. So we have the list of the head, and we want to see the distribution. So here we will make the bin equals to 5. So every 5, we want to check how many of them. It means now the head of the tree between 60 under 65, we have 3. The head in between 65 under 70, we have also 3. The head in between 70 under 75, we have 8, and so on. So this is the frequency from the numerical data. It is to show the density and the distribution of continuous numerical data. Note that bar chart plots categorical data. Okay, that's the basic one. Scatter plot. The scatter plot, it is good to show one variable that affects two other variables, or it is to show the precise data dense visualization, correlation, and clusters between two variables. And mostly the data are two numerical variables. So we already see from the orange. We want to plot the petal length and the petal width. So those two are numerical. So in this case, yeah, we will check more data about this one. This is the data about tips. Do you know tips? If you go to a restaurant in USA, you need to pay tips to the waiter. So you need to give some money. If you feel that you are happy with the service, you will pay more tips. But maybe if you are not satisfied, you will pay just very small tip. So the restaurant, like, they want to get some feedback. How much tips the customer pay? And they also save the data about the total bill. So they want to know whether there is a correlation between the total bill and the amount of tips. So this is the data. And they can also distinguish whether the tip is given on the dinner time or the tip is given on the lunch time. So it is numerical tip, okay, the amount of money that you give, and the total bill also, it is numerical, the amount of the amount of bill that you need to pay to the restaurants. So we can also use another numerical variable, the third. So if there is another variable which is numerical, you can make a bubble chart. The third variable changes the size of the dots. So you can see that this dot have the same size, but if you have another numerical variables, it will change the size. So let's see in the orange. I think you already see most of those graph. Okay, you already see the distribution. Okay, in the distribution, yeah, as I explained to you, you can select the bin width. If the bin width is 1, it means you want to plot in the range of 1. So 4 until 5, 5 until 6, 6 until 7, 7 until 8. And then you can calculate how many frequency of the data in this range. This is the histogram. And let's say I want to see the bar plot. The bar plot means the categorical data. Is there any categorical data? Unfortunately, we don't have categorical data in this case. So orange will plot every data. So it plots every single data into the Y. So the Y here is the sepal length. It shows for every single instances about the length. You change the sepal width, then it shows every single data about the sepal width. So there is no categorical data. That's why it shows like this. The scatter plot, yeah, we just look at this one. We have the regression line to represent whether there is a correlation between the two data. We can also give the color region like this one. So it is about the clustering. So later we will learn more about this. But what I want to explain this one is about the bubble chart. Here it mentioned that when you have a third numerical variable. Now we have only two. Okay? We have only two, which is petal length and petal width. Let's say I want to check also with the other attributes, maybe sepal length. You can see that now the size changes. Maybe it's not that obvious, because the number is very small. So if you make it a little bit bigger on the symbol size, then you will see that this size is higher or bigger than this one. It's very small. So the bigger size means the bigger sepal length, and the small here means the small sepal length. So we have three kind of variables, and we call this is the bubble chart. I will explain this one heat map after this one. We have the pixel oriented visualization. What is the meaning by pixel? Usually we can make the visualization in terms of colors. What I just explained to you in the scatter plot, we can make a different color. And you will see that the color is a little bit degraded. For example, here is darker. Here is a little bit light. So it means there is no data. The dark red means the data is in that area. The light red, yeah, we have no data. So something like that. Or sometimes we can also say like this one, income, credit limit, transaction volume. The light color shows the small income. The dark color shows the higher income. And we know that maybe it is dominant to the higher income, maybe not. Okay, it's not, we cannot see the dominant. But here, the credit limit, the darker is very small amount, is more on the light green. Okay. Then maybe for the credit limit, there are many small credit limit than the high credit limit. What about the transaction volume? Okay, in the middle, it shows dark. Then there are many transaction volume in this area. But small transaction volume or high transaction volume is very small. Maybe if we look at the distribution will be something like this one. Small is very less and the high transaction volume also less. So this is the meaning by the pixel oriented. We can use also heat map. In the heat map, we can see directly about these figures. It shows the general trend. It is the data about the temperatures, okay, average monthly temperatures at the Central Park, New York. And the data will be about two numerical or categorical variables. So the third variable is often the number of data points associated with the particular row or column. And then it is encoded as the color of the cell. So if you look at this one, in New York, in January, it shows green. We know that New York has the same area with Korea. So in the winter time or in January, it's winter. So the temperature will be very low. And on July or August, so the temperature will be high. So it becomes red. And based on the average monthly temperature, we can see that in 2010, or yeah, somehow here, the temperature is the highest among the other. And based on this graph also, we can see that in 2011, yeah, it shows the lowest among the others. This heat map can be also done in the orange. You can make the heat map here. So you can easily look at the variables here, sepal length, sepal width, petal length, and petal width. And the color represent the numbers. If you look at this scale, the blue means very small and yellow means the highest. So if the color is becoming more yellow, then the size is high. If the color is more on blue, then it is small. So we can see directly from this heat map about the data patterns or the data distribution. And in the maps, okay, we call it choroplets. It is best used for the spatial patterns. So like this one, we can see the population. In US, maybe this is the number of vehicles per 1,000 people in 2015. So if the color is darker, then the number of vehicles is higher. And the maps or choroplets, it is mostly used in the maps. Okay, we have the X, Y, or longitude, latitude. We can have the address or the place name. It is usually the one numerical variable or one categorical variable. Okay, I think I will stop here because of the time.